Welcome everyone to this DCC training on FAIRification of terminologies. This is a very important topic, and I'm very happy that we have today Deepak Oni from our team, who will actually really present you all the challenges which come with the use of different terminologies and what you can actually do to verify them. And I think just a few words in the beginning. I think quite often you've seen that you may not have the choice about which standards you use, because there is some standards which are already used in your data. And quite often it's then quite hard to use that standards. And that's really why we in SPHN were really thinking hard about how can we make these terminologies fair, or you always have to say fairer, because it's always hard to reach the absolute fairness. And this, of course, will really help us at the one side that the data which use that standards can be understood by secondary parties, but also for yourself, it will really help you to make use of the information which is in this terminologies, for example, the hierarchies, when you do analyze the data, when you query the data. And also, last but not least, it helps a lot for also doing quality control on the data. But with that, without further ado, I would like to hand over to Deepak, who will really dive us deep into that topic of FAIRification of terminologies. Thanks a lot, Deepak, and the floor is yours.
Thank you, Sabine, and thank you for the lovely introduction. So let's start with maybe the basics, which is looking at the FAIR principles. And I'm sure most of you are already aware of what the FAIR principles are, but just to put everyone on the same page here, FAIR principles are a set of guidelines that to make research data findable, accessible, interoperable, and reusable. These principles were originally introduced back in 2016 as part of the FAIR guidelines paper by Mark Wilkinson. And by findable, we mean that the research data should be easy to find for both humans and machines. And by accessible, we mean that research data should be openly available and accessible to anyone who wants to use it. By interoperable, we mean the research data should be structured in a way that allows for it to be combined with other data sets. And by reusable, we mean that the data should be usable for different purposes and by different researchers. And this slide gives an overview of all the guidelines for each FAIR principle. To ensure data is findable, we need to make sure that both data and metadata are assigned unique persistent identifiers. To make sure data is we have to make sure that data is described with rich metadata, and that metadata is explicitly linked to the data that it describes, and that the metadata should also be indexed and searchable in a public resource. To ensure data is accessible, we need to make sure that the protocol used to access the data is open and universal. And we also need to make sure that this protocol supports authentication and authorization where needed. And the metadata should also be accessible when the data is not, for historical purposes and long-term availability of what was there before. And to ensure data is interoperable, we need to make sure that both metadata and the data, if possible, uses a formal and accessible language for knowledge representation, and that metadata makes use of vocabularies that themselves follow FAIR principles, and that metadata makes qualified references to other metadata so that it's easier to ground your metadata elements in terms of externally available metadata. And to ensure data is reusable, we need to make sure that the provenance and the data usage license is clearly captured and described. Now, as we progress through this presentation, I will make some recommendations on how to put these guidelines into practice. But first, let's look into a quick introduction on semantic standards. Semantic standards are a way of capturing and representing knowledge about a particular domain. There is a spectrum of semantic standards, as you can see on the right in the figure, and depending on its complexity and the semantic clarity that it provides. With the higher the semantic clarity, the greater the expressiveness, structure, and inferential power that you get from that semantic standard. For example, the control vocabularies and thesaurus being simple and ontologies being more complex in terms of how it's organized, but yielding more higher semantic clarity. And the choice of semantic standard really depends on what your use cases are, the type of data you are working with, and also how vital semantics are for your application. Now, there are several types of semantic standards, but for the sake of this presentation, we will talk about control vocabularies, monohierarchical classification, polyhierarchical classification, and ontologies. And collectively, we refer to semantic standards as terminologies. Now, a control vocabulary is a collection of terms predefined and arranged for a specific purpose. These terms are usually associated with a label that describes the scope and meaning of those terms. And the terms may or may not be organized hierarchically. And control vocabularies make it easy to categorize data using the terms and also to search and retrieve data using the same terms. And this is kind of, if you think about it, like tagging your data with certain terms, you would find these tags from control vocabularies. Then the next type of semantic standard is a classification, also known as a taxonomy. And a classification applies a hierarchical classification scheme that groups terms together based on some characteristics or attributes. And the terms are usually arranged from more broader term to more specific term as part of the hierarchy. And this is very useful for classifying data based on their characteristics, which are typically captured by the terms in the classification and how they're associated with the data. And there can be two types of classifications depending on the hierarchy. We have a monohierarchy, where there is a single link between terms indicating a hierarchical parent-child relationship. And we have a polyhierarchy, which is a type of classification where there are multiple links between terms. For example, a single term can have multiple parents. And this is a more complex type of hierarchical organization, which is expressing something more complex than what a monohierarchy would be able to. The other type of semantic standard is an ontology. And there are several definitions out there for an ontology, but the one that I found to be more comprehensive would be an ontology is a formal specification of concepts from a particular domain of knowledge that are arranged in a hierarchy as a directed acyclic graph where concepts are defined in relation to other concepts in the graph. So you're not just capturing hierarchical relationships, but also capturing some complex relationships on how some concepts relate to other concepts that actually is a way of modeling the information that you have in that particular domain. And the language of choice for ontologies is the Web Ontology Language, or OWL. And ontologies that are defined in OWL are machine readable, where the concepts are defined in such a way that they can be parsed by machines. And they support reasoning because the concepts follow certain semantic rules, and it is possible to reason or really validate certain assertions that are made as part of these rules. And also ontologies support inferences where machines can infer implicit knowledge based on the existing concept definitions and rules. Examples of ontologies can be SNOMED CT, sequence ontology, genotype ontology, just to name a few, but there are several out there that are being used actively within the biomedical domain and also other related domains. But not all semantic standards are represented as an ontology or using a formal knowledge representation language. Some can exist in spreadsheets, CSV, or even free text. And these are usually easy for humans to read and understand, but they can be difficult for machines to parse because there is no firm structure that is being imposed, or there is no firm knowledge representation that is being used for a machine to be able to parse this information. And so it is possible to adopt best practices and make use of W3C standards to build your own formal representations of these terminologies so that you can use them as part of your project. Because let's say terminologies exist as a CSV, it's difficult to make use of these terminologies as part of a more broader semantic interoperability strategy as we faced here in the SPHN. And so if done properly, you can adapt your terminology such that they are both human and machine readable, and also they conform to FAIR data principles. That means you are making a conscious effort to provide these terminologies in such a way that you're translating the terms from the terminology into concept classes. You're representing hierarchical relationship via parent-child relationships. And you are also representing definitions, synonyms, and mappings if they are provided by the upstream terminology. And by providing this translated version for yourself and for others to use, you are also making an active effort to support your community with these terminologies. But you have to make sure that the license permits you to do so, because when you redistribute terminology in RDF, you are in a way redistributing that terminology, and that license should support redistribution as well. Now, in the context of SPHN, there are two ways terminologies are provided. The ones provided by the SPHN Data Coordination Center, or the DCC. These are the terminologies that are used as part of our semantics. For example, we use SNOMED-CT and LOINC for meaning binding, and also SNOMED-CT for value set binding. And so these are the terminologies that we are relevant for SPHN, especially as part of the SPHN semantics. And some already exist in RDF, for example, sequence ontology and genotype ontology. So we don't have to do anything in particular to FAIRify these terminologies. But there are others like ATC and CHOP or ICD-10-GM, which we need to bring and we need to FAIRify for it to be used as part of the semantic interoperability strategy in SPHN. And there are also terminologies that are provided by the SPHN projects. These are the terminologies that are useful as part of the project-specific semantics. And so a project might rely on a new set of concepts that needs to be mapped to a new terminology that may not be provided by SPHN. And so the project is sort of taking the responsibility of providing this terminology in RDF. Now, to talk about terminologies in SPHN, there are quite a few. For example, the SPHN DCC provides the anatomical therapeutic chemical classification, that is the ATC for chemical substances. Then there's CHOP, which is the Swiss classification of operations and procedures for procedures. There is the ICD-10-GM, which is the International Classification of Diseases, the 10th revision German modification for diagnoses. The systematized nomenclature of medicine clinical terms, SNOMED-CT for clinical terms. Then we have LOINC, which is a logical observation identifiers, names, and codes for laboratory tests. UCUM, that is the unified codes for units and measurements for units. Sequence ontology, or SO, for a lot of for representing information about sequence features. Then genotype ontology, or genome, to represent information about genotypes associated with variants, and then HUGO or the HGNC for representing names about genes that are typically standardized for humans. And I presented the slide earlier, which is a set of guidelines for implementing the FAIR principles, and each guideline can be implemented in a particular way, depending on how you interpret them. For example, for findability, you can use unique and persistent IRIs for each concept in the terminology. And you can also be sure to capture and represent as much metadata as available from these terminologies. And you can link your terminology concepts to other metadata elements. And you can also provide a way for this metadata to be searchable on the web, for example, by providing them as publicly available terminologies. For accessibility, you can make use of HTTPS IRIs that are resolvable where possible. And you can also ensure long-term availability by providing current and previous versions of the terminology for your consumers. For interoperability, you can use RDF as a data model for knowledge representation. And by adopting RDF as a data model, you're also able to use existing semantic web standards like RDFS, SCOS, and OWL for modeling a lot of your concepts and the semantics of these concepts. And also you can link your concepts to other external concepts. This is typically useful when you have some mapping information available where you can map a term from a terminology to an external terminology. And also for reusability, you can make use of the Dublin core vocabulary for representing copyright and license information, which is always useful and important because it clearly states how this terminology can be used by downstream users. Now, a lot of these guidelines and suggestions may seem abstract, but let's put it into practice by taking a look at how we here at SPHN DCC apply these guidelines for one of the terminologies, which is the ATC. Now, the ATC is a drug classification that categorizes active substances of drugs according to the organ or system where their therapeutic effect occurs. It is a monohierarchy, and the hierarchy consists of 5 levels, going from broader to more specific. So level 1 being the anatomical main group, level 2 being therapeutic subgroup, level 3 is pharmacological subgroup, level 4 is chemical subgroup, and level 5 being chemical substance. And the way the terms in ATC is formatted is that the semantics and the level is part of the code itself. And you will see how we break that down in the coming slides. And here's a sample code from ATC. We have A02AB03, which is the code. And the name for this code is aluminum phosphate, which has apparent aluminum compounds, which has apparent antacids, which has apparent drug for acid-related disorders, which again has apparent of alimentary tract and metabolism. So this hierarchy is reconstructed here on the right, where you can see it's going from the most specific term to the more general term. And this is one such hierarchy, and ATC consists of thousands of such hierarchies that describe different chemical compounds. But in reality, this is what the actual data file provided by the World Health Organization looks like for ATC. It is an Excel spreadsheet where you have columns, and the codes are on the first column, and then there is a level name, which corresponds to the label of the code, and then some additional metadata that might be relevant for this particular code. But then you can but you can note that there's something missing here. First of all, there is no unique identifier that refers to each code. There is no formal language for knowledge representation. We can look at the Excel spreadsheet and guess what they all mean, but then there is no formal documentation that actually explains how this is structured. There are no machine readable hierarchies. We can look at the code and we can see that because this is A and then A02, A02A, just by the way the code is structured, we can guess that they are part of the same hierarchy. But it is difficult to access this programmatically because these rows are together for this example, but in reality, these rows are all far apart from one another. So you won't be able to just parse them line by line and figure out the hierarchy. And there is no metadata about ATC as part of this Excel file. Like, for example, there is no information about the license, there's no information about the version. And so there is a lot of extra work that goes into parsing and understanding what this terminology is trying to say and how it can be used in the context of RDF. So there are some practical ideas that we can put into place. For example, we can make use of a unique and stable IRI for ATC. And this is typically possible if we use an IRI from the terminology provider. So in the case of ATC, the WHO provides a stable IRI already, which refers to the ATC code where at the end of the RRI, if you put the ATC code, it would resolve to a resource on the World Wide Web. So we would recommend using a stable IRI if it's already available from the terminology provider. And then we would make use of a version IRI to denote the version of ATC. In this case, we are creating our own IRI because we are referring to the version that we are providing in RDF. And in this case, we are referring to the 2022/1 version of ATC. And then we can represent each concept from ATC as an RDFS class. And each concept name or label can be represented using RDFS label. And hierarchical structures can be represented via RDFS subclass of where we are saying the child is a subclass of the parent. And we can also, and it is recommended that for terminologies that don't have a grouping node at the top level, to have a root node that links to, that acts as a super parent of all the hierarchies defined in ATC. And this is typically useful so that you can collectively refer to all the codes from ATC by using this root node. So in this case, we would have a root node called ATC. Now here's the quick Python code that will take into consideration the previous recommendations and create the RDF representation for codes from ATC. And this resource will be, the script will be made available as part of this webinar. And so you can run the script yourself as well. But just to break the script down into parts, first you're setting up the graph with the general metadata that is needed for any type of RDF graph. And in this script, we are making use of rdflib, which is a Python package for working with RDF data. And we are importing the necessary vocabularies that we will be using, like RDF, RDFS, OWL, and Dublin core. And then first, we're defining a namespace for ATC, which is, again, what we are doing, where we are using the IRI provided by the WHO. And then we will define as SPHN specific namespace for ATC. This is the one where we say, where we mint our own IRI for this resource. And then we instantiate a graph, an rdflib graph, and then bind certain vocabularies that we want to be using, like RDF, RDFS, OWL, and Dublin core. And then we would define a version IR. So the next part is where we are setting up the graph with the terminology specific metadata. So for example, we define the ATC version, and in this case, we're defining it as 2022/1. And then we will define a root node. And as I mentioned earlier, we are having this root node just to link all the codes in ATC under one tree. And then we would add some terminology specific metadata, like the title and the copyright information, so that this information is already there as part of the RDF graph. And then we can start building the graph, where we add first the root node, that is we add the root node as a RDFS class and give it a proper label, that is ATC. That's the one you see here. And then we will add the first term of this hierarchy, which is the elementary tract and metabolism term. And then we add it as an RDF type class and give it a label, and then say it's a subclass of the ATC root. And then we add the second term, and then we add that as a subclass of the first term. And then we keep doing this until we go down to the end of the hierarchy. Now, this is a very deliberate example, and it is very oversimplified. In the real case, when you're working with ATC, you will be parsing the files directly as provided by ATC, and scaling up by creating thousands of codes and reconstructing the hierarchies yourself. But this is just for the sake of this example. And if we were to export this graph into RDF Turtle, which is a serialization format, one of the serialization formats for an RDF graph, you would see the following, where we have an ATC node with the label ATC, which is of type RDFS class, and then ATC-A with a label elementary tract and metabolism, which is a subclass of the root node, and then ATC-A02, which has a label drugs for acid-related disorders, which is a subclass of ATC-A, and then we keep going down the hierarchy until we get to the most specific term, which is ATC-A02, AB03, which is aluminum phosphate. And this is how we provide our terminologies in RDF in a similar sort of approach. And we do this for CHOP, ICD-10-GM, LOINC, and UCUM. But as I mentioned earlier, there can be terminologies that projects might need that are not offered by SPHN DCC. And in some cases, some of these terminologies may already be available in RDF. For example, a project might need to use the orphanet rare disease ontology or the human phenotype ontology. And both of these are available in RDF as an OWL file that they can use directly. But in some cases, it is entirely possible for a terminology to not exist as RDF. And in this scenario, projects can use the same approaches that we highlighted earlier to bring their terminologies of interest into RDF. And projects can make use of existing resources to guide their efforts. For example, we have a documentation where we describe how to FAIRify external terminologies for projects. And this is up as part of our Read the Docs documentation. And we also have an example Jupyter notebook that brings a sample terminology into RDF, following the similar approach that we just saw a couple of slides ago with the Python example. And we also have an ontology pipeline that is openly available that shows how we actually do it in practice, where we translate ATC, CHOP, ICD-10, GM, LOINC into RDF, and these are also used as part of our terminology service. But there are some things to keep in mind when you are working with terminologies. And these are some of the lessons we learned along the way, and it deserves to be mentioned in this particular context. When working with terminologies, one can make certain assumptions about the terms as they are represented in the terminology. For example, you can assume that in the case of term removal, terms are never removed from successive versions of the terminology. That means that if a term exists in the 2020 version of a terminology and it is retired in the 2021 version, then it is not removed from the 2021 version. In the case of term recycling, one assumes that terms are not recycled between two versions of a terminology. So if a term exists in the 2020 version and it is retired in the 2021 version, then the assumption is that this term is not reintroduced again in 2022 with a new meaning. And in terms of term consistency, one assumes that the terms defined are unique and consistent within the same version and across the versions of a terminology. So if I'm referring to a code in the 2020 version of a terminology, then the same term exists in the 2022 version with the same meaning. But there can be scenarios where this has not been the case for some terminologies. And so starting with these assumptions, while reasonable, might be risky. Now let us consider an example with ATC. In the 2016 version of ATC, we have a code called C07FP02, that is a code ID, with the label metoprolol and other antihypertensives. This code was split from one code into two codes in 2017, into two codes, that is metoprolol and felodipine, and metoprolol and amlodipine. And you can see how the code C07FP02 was retained for metoprolol and felodipine, even though the meaning changed between 2016 and 2017. And then a new code, C07FP13, was introduced, which had a different meaning, or slightly similar meaning. And you can see how the scope of the code from 2016 changed, and it became more specialized in 2017. But there are some consequences of a change such as this. So now we know the semantics changed between 2016 and 2017 for this code. And if someone coded their data to C07FP02 in 2016, and the code changed in its meaning in 2017, then they would not be aware of this change unless they did the coding again, which is not always guaranteed, because there can be data providers who do the coding every other year. And so this information would not be, they would not know about this change unless they did the coding with another future version of the terminology. And so a change such as this affects coding practices, and it affects the data consistency from a user standpoint. And it also affects the semantic clarity of the code, since the same code can mean slightly different things depending on the year you're referring to that code. And this is more pronounced when you provide the terminology in RDF, because when you do translate these terminologies in RDF, you are taking the responsibility of providing these terminologies in an unambiguous and consistent manner. And since your users will also start making use of these terminologies as part of their data pipelines or analysis or querying. And so we found out about ATC last year, about this inconsistency. And let's take a scenario where we are focusing on the 2017 version of the C07FP02 code, which is metoprolol and felodipine. And a researcher assumes that the data was coded with ATC 2017 or later. And from a querying standpoint, the researcher wants to exclude metoprolol and amlodipine. That is the other code we saw in the previous slide. And they want to exclude all the results that are linked to this code. And so they're querying only for data associated with metoprolol and felodipine. If the data provider had sent the code to ATC 2016, then the researcher will not know that the results are also including the data that corresponds to metoprolol and amlodipine, which is completely against what their original query was. And this is not something we just observed in the case of ATC. you can see we did a comparative analysis where we compare successive versions of a terminology. And for ATC, when we compare the 2016 with the 2017, we see 7 codes that change in its label and meaning. And when we compare 2017 to 2018, we see 8 codes that changed in meaning. And between 2018 and 2019, we see 9 codes. And in between 2019 and 2020, we see 6 codes that change in its meaning. But this, and it's kind of the similar trends for ICD-10 GM, but this is far more pronounced in the case of CHOP. And so it is not just a problem that plagues one particular terminology, and it all boils down to the fact that you need a strategy for tackling these issues, and especially when you are intimately working with these terminologies yourself. And so in such scenario, it is recommended to adopt a versioning strategy for your terminologies. And there are several approaches to versioning terminologies. Excuse me. But the one that is easy to implement and effective would be to first assign a version to each term from a particular version of a terminology, and then apply a strategy for identifying terms that are identical between versions. So you're starting out with the assumption that no 2 code is identical across versions, and then you're really deliberately trying to establish identity between codes across versions. So the easiest approach would be to look into lexical match, where you're comparing the label of one code in one version of a terminology against the label of the same code in another version of the terminology. And the more complex approach would be to look at the semantic structure and compare the semantic structure of the code between versions. And this is a bit more complex because you are taking into consideration not just the label, but also where the term is organized in a hierarchy and any additional metadata like synonyms or mappings that might be available for that term. But let's assume the simpler approach, the lexical match. Going back to the ATC example again, first, we start off with assigning the version to each term. So now in the 2016 version we are assigning the version as part of the identity of the code. So we're uniquely identifying C07FB02 from 2016, and we're doing the same for 2017. At this point, we have not made any statement about which terms are identical to one another across versions. And then we apply a way to establish identity. In this case, we take the simpler approach of just checking their labels. And we see that metoprolol and other antihypertensives is not the same as metoprolol and felodipine. And it's not even the same as metoprolol and amlodipine, even though they might be similar. And so we mark these two terms as separate. We don't establish any identity between the two. But there can be terms that are actually identical based on their labels. So the code C07FB02 has a parent C07FB. And let's assume that the label of C07FB is the same between 2016 and 2017. Then we can mark the two as equivalent here in the 2017 version, but then we don't say the same for the C07FB02. And since C07FB13 was introduced in 2017, there is nothing to compare to back in 2016. Now in RDF, this is how it would look like, where we have a small snippet of RDF data here, or RDF representation of ATC. This is again the same code from 2016. And in 2017, we are repeating the same information, but we're also representing the 2017 version of the same code, but we are not saying that they are identical yet. And then, but we know that C07FB, which is the parent of C07FB02, is identical based on their label. And what we're doing here is we are saying that the code from 2016 is a subclass of the code from 2017, and the one from 2017 is a subclass of the one from 2016. This is just an easier way or another way of representing our equivalent class, where you're saying the two codes are identical to one another. And you would do this for all codes that are identical, and you would not do this for any code that changes in its meaning between versions. And then you can apply the same approach for future versions of the terminology. So here we're looking at the 2018 version. And so you can see just from this example here that the code from the 2016 is preserved in 2017, and the one from 2017 is preserved in the 2018. So you are really trying to keep a comprehensive catalog of all the terms that are in the current version and all the historical versions. Now, applying such a strategy would allow you to identify and manage term removal because you know what's happening to each term across the different versions. And then you're not surprised when a code does not exist in a new version because that same code does exist as part of your release of the terminology. And you can also identify and manage term recycling because if a term was recycled, that term wouldn't be the same for, when you compare it to the previous versions of the terminology. And it also helps you establish some semblance of consistency because now you are applying some additional approaches to ensure that the terms are consistent across versions. And also, your users can also refer to the terms from previous versions of a terminology. But all of this is only possible if your data providers and users or researchers are actually using the versioned IRIs for your codes. So that is also an important aspect of this versioning strategy. So now that was a lot to talk about, I'm sure, and that was a lot of approach, and these approaches usually have worked well for us so far. But then what next? In the context of the SPHN, projects can provide their terminologies in RDF, and these project-specific terminologies can then be utilized as part of the project-specific semantics by defining it in their own data set. So the SPHN provides a dataset template that is a way of projects to add new concepts or extend existing SPHN concepts to build a project-specific RDF schema. And as long as the project-specific terminologies are accessible in RDF, then even the users should be able to leverage these terminologies for querying, analyzing, and exploring data that conforms to the project semantics in addition to the SPHN semantics. Now I want to leave you with some resources as we reach the end of this webinar, some resources as a follow-up to this topic. For example, we have the ontology pipeline for terminology service, which is a place where you can look at the existing pipelines that we have that are used by the terminology service for converting and FAIRifying terminologies in RDF. We have the terminology service itself, which is a place where you can download the terminologies that we provide as part of the SPHN DCC. We also have documentation on external terminologies that are already in SPHN. And these are the ones that I mentioned, like ATC, CHOP, sequence ontology, genotype ontology, and so on. And we also have documentation on FAIRification of external terminologies in RDF. And this is where we really go through an example of how to convert an example terminology into RDF, just like the example we saw earlier. And we also have an SPHN dataset template. This is what projects would use for building their own semantics and using the terminologies that they provide in RDF as part of their semantics. And we also have a documentation that provides projects with an easy setup on how they can build their semantics using this dataset template. Yeah, so with that, I would like to conclude this webinar, and we can move to question and answers.